Good morning and welcome back. Everything goes well these next 2 days. These are our last 2 days of lecture, new content. Next Monday, review. The following Wednesday for the in-person sections is the ACS exam in the front half of the class, and then review for the second half of the class. I'm a little sad about it, but I might be the only one. You guys might be looking forward to the end of the semester. That's okay. Let's talk about these problems. At room temperature, some compound A is a gas and some compound B is a solid. Which compound has stronger intermolecular forces? Raise of hands. Ryan, I thought you were going to change your pace at the end of the semester and not raise your hand. What do you say? B has stronger intermolecular forces because it's a solid. How can we justify Ryan's answer? Cole? I really like the concept you just brought up. Gases have more energy than solids. And those with more energy, they overcome those intermolecular forces. Is that necessarily true that gases have more energy? What is energy proportional to? We talked a lot about energy, so this is a good discussion for us to have. Energy is proportional to what? Temperature. And what do these two compounds have in common? They have the same temperature, which means they have actually the same amount of energy. So compound A has enough energy that it exists as a gas. Compound B with the same amount of energy still exists as a solid. It's using that energy in different ways, or it's experiencing that energy in different ways. What difference do they have in their experience? A is not interacting with other molecules of A. That's what we define as a gas. It's spread out, it doesn't interact with other molecules, whereas B is not just closely interacting with other molecules, that would be a liquid, it is tightly interacting with other molecules. B cannot overcome the interactions with other molecules, despite having the same amount of energy as A. The way that energy shows up looks different. Molecules of A are moving around a lot faster, and so that energy is put into kinetic motion, whereas molecules of B aren't able to move, so they're actually just vibrating in place. They're just buzzing next to each other, vibrating. They're using the same amount of energy to vibrate as those gas molecules are to move around, but that energy of vibration is not enough for compounds of B to get past other molecules of B. So we had two different answers, I think, right? Cole, you kind of originally said A must have more energy than B. Maybe not actually answering the question of intermolecular forces. Do you feel like you have a different perspective now? We don't know anything about their bonds. Yeah, actually their intramolecular forces are a huge question mark for us. Don't know if they're ionic bonds, don't know if they are covalent bonds, polar covalent, non-polar covalent. Nothing intramolecular to be known. Only intermolecular can we interpret here. Yeah? So this is really, when we say compound A is a gas, compound B is a solid, we're describing the experience of each molecule. We're saying A does not experience interactions with other molecules of A. B strongly experiences. So which has stronger intermolecular forces? A, B, or not enough information? B. B cannot overcome the intermolecular forces to escape all of the other molecules and become a gas. B has stronger intermolecular forces than A. We can't make this assertion if we don't know that they're at the same temperature. So that was a huge point for us here. All right, what about this? Water and sugar. Which has stronger intermolecular forces? Are there any assumptions that you feel like are missing? Is there not enough information? What assumption would you like to make about this question? If they're at the same temperature, which one has stronger intermolecular forces? Good. What would you say? Sugar. Why? Let's say the temperature is room temperature. What do you experience water as? And sugar as a solid. So for the same principle as above, something that is a solid must interact with other molecules so much that it can't get away from them. So sugar has stronger intermolecular forces than water. And if we look at their structures, I'm gonna draw the structure of sugar using some assumptions. This is what we call a bond line structure. And bond line structures assume carbons at every end and every bend, and they assume enough hydrogens at every carbon to satisfy its octet or satisfy its charge. So this is a simplified structure. And then here's water. What do you notice about water and sugar? What intermolecular forces do they have in common? They have hydrogen bonding in common, which also means that they have dipole-dipole in common, because hydrogen bonding is actually just a specific subset of very strong dipole-dipole interactions. Does that mean that they also have dispersion forces in common? Yeah, everything experiences dispersion forces. What about this? Which of these compounds experiences more dispersion force? We said dispersion force increases with increasing size and surface area. Which of these compounds has more intermolecular forces from dispersion? Sugar. Which of them has more intermolecular forces in the form of hydrogen bonding? Also sugar. Water is unique because for its incredibly small size, it packs a lot of hydrogen bonding. Both hydrogens can be involved in a hydrogen bond, and the two lone pairs of water's oxygen can be involved in a hydrogen bond. So water can hydrogen bond up to 4 times per molecule, despite having just 3 atoms. Whereas sugar can hydrogen bond from each of the OH groups, and also the oxygen in the ring can hydrogen bond if there's another H somewhere in the structure connected to an O in the sample. So sugar has a lot of hydrogen bonding, but not as compact as water's hydrogen bonding. Okay, so one thing that I want to point out from this problem when we look at sugar and water is that intermolecular forces are a compounding effect. We say that hydrogen bonding is the strongest, but if you get a ton of just dispersion forces, that can outcompete hydrogen bonding. If we take, for example, water, which we know has a lot of hydrogen bonding, but not a lot of dispersion forces. And then we look at something like butter, which predominantly a solid at room temperature. Again, I'm going to use bond line structure here to simplify this chain. Butter has a very long hydrocarbon chain capped off with this polar part of the structure. Very little hydrogen bonding, but a ton of dispersion forces. So despite hydrogen having 4 hydrogen bonds per molecule, this potentially having a few, this has a lot of dispersion. one thing you should be able to do from our learning in this section is rank the types of intermolecular forces. Dispersion is a much weaker force than hydrogen bonding, but also recognize that these are compounding effects. So despite having less hydrogen bonding, it has a lot more dispersion, and that actually increases the intermolecular forces in things like butter, other fats, even plastics. A lot of plastics only contain dispersion forces, but their molecules are so long that they get a ton of dispersion forces that really increase their intermolecular forces. Let's answer these other two questions quick, and then I have one more example I kind of want you to look at with you guys. If oxygen dissolves in water, which intermolecular forces are present between solute and solvent? What's the easiest one? Dispersion forces exist between molecules of molecules of oxygen and molecules of water. They experience dispersion forces between each other. Do they experience dipole-dipole forces? Meaning a dipole on water interacts with a dipole on oxygen. Where's the dipole on O2? Which way does it point? Which part of O2 is more polar? More negative? Which side is more positive? No dispersion force. Only dispersion force, but no dipole-dipole. What about hydrogen bonding? What are the rules on hydrogen bonding? Hydrogen bonding is a specific interaction between the hydrogen attached to what three atoms? Fluorine, oxygen, nitrogen. Hold the phone. And the lone pair on a fluorine, oxygen, or nitrogen. So do you think that hydrogen bonding can exist here? Is there a hydrogen connected to a fluorine, oxygen, or nitrogen? Yeah, definitely. And then is there a lone pair on a fluorine, oxygen, or nitrogen? Technically there is, right? Unfortunately, I pulled this one out of my back pocket, never thought of it before, tried Googling an answer because my chemical intuition, my understanding of how oxygen interacts with water would suggest to me that there is not hydrogen bonding. If there was hydrogen bonding, that would lead me to believe that oxygen would dissolve in water fairly well, and oxygen does not dissolve in water very well because there are not good intermolecular forces. And yet this kind of meets our criteria, right? So I think there is a component to that hydrogen bonding criteria that we need to add, which is hydrogen connected to a fluorine, oxygen, or nitrogen interacts with the partial negative lone pair on a fluorine, oxygen, or nitrogen. And this oxygen does not have any partial negative. If hydrogen bonding is a subset of dipole-dipole, just a very strong dipole-dipole force, then this doesn't actually meet the requirements for hydrogen bonding because there's no dipole on O2. So there's no strong partial negative on either of those oxygens to partake in the hydrogen bonding. It seems to meet the criteria, but it can't meet the criteria at the same time. So that's a change that I wanted you to think about. No partial negative means no dipole-dipole, no hydrogen bonding. We could say the same thing with nitrogen gas, N2. Nitrogen gas has a lone pair on each nitrogen. That would suggest that that can participate in hydrogen bonding with water, but it doesn't because there's no partial negative. And that partial negative created by a dipole is crucial for the hydrogen bonding. What about methane, natural gas dissolved in water? What type of intermolecular forces are here? Dispersion. It can't not have dispersion. How about dipole-dipole? What do we need to analyze to understand if it can have dipole-dipole? Polarity of both of them? What do we know about water? Polar or nonpolar? Polar. Methane, polar or nonpolar? Let's run through our rules. Does methane have any polar bonds? The CH bond is listed as nonpolar. Okay, that's it. Now it doesn't matter. If there are no polar bonds, then it can't be polar, so it does not have dipole-dipole forces with molecules of water. What about hydrogen bonding? Can the molecules of water interact with the hydrogens on methane? You want to explain why? Good. This molecule, also nonpolar, meaning it wouldn't be able to do hydrogen bonding anyways, doesn't even fit the requirements of hydrogen bonding. And I actually see this a lot, especially when students get up into my organic classes, because we look at these types of molecules a lot, and they say hydrogen bonding, an interaction between lone pairs of one molecule and hydrogens on another molecule. These hydrogens do not experience hydrogen bonding ever, because the CH bond is not polar enough to create for that strong dipole-dipole moment that's needed for hydrogen bonding. A CH hydrogen never involved in hydrogen bonding. So, no hydrogen bonding here ever. Okay, back to this idea of compounding effects of these intermolecular forces. I want us to look at this series of molecules and rank them by their predicted intermolecular forces. We'll have water, methanol, ethanol, isopropyl alcohol, and butane. H2O, CH3OH, CH3CH2OH, CH3CHOH, CH3, CH3, CH2, CH2, CH3. We have to go through and consider pure samples. So a sample of just water, a sample of just methanol, just ethanol, just isopropanol. Which of these would experience the strongest intermolecular forces within a pure sample? It might be challenging to say which of these has the strongest. It might be easier to say which of these has the weakest. Which compound here experiences the weakest intermolecular forces in a pure sample? Water experiences the weakest intermolecular forces. Butane. We know what all of these compounds have in common, correct? They all experience dispersion. So this has dispersion, this has dispersion, 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 dispersion. Is there any other force that butane experiences? No. There are no polar bonds, so there's no dipole-dipole forces, and there's no capacity for hydrogen bonding. Doesn't meet the requirements. All of these others have dipole-dipole moments, interactions, and hydrogen bonding. So this is our lowest. Let's set this at number 5. Now we're comparing all of the compounds that have some capacity for hydrogen bonding and ranking them against each other. Water seems to be an outlier here, correct? Water is the smallest of these molecules, but like we said earlier, water can actually experience a lot of hydrogen bonding. Both of the H's in H2O experience hydrogen bonding, and both of the lone pairs. When I remove one of those H's connected to the oxygen and I substitute it for this carbon chain, I actually decrease how much hydrogen bonding can happen. This experiences the most hydrogen bonding per molecule, which means this is the compound with the strongest intermolecular forces. Do you guys agree with that? Do you disagree at all? Water experiences the most hydrogen bonding per molecule? Does it feel hard to justify? If all of the compounds have the same amount of lone pairs on the oxygens, and all of the compounds have at least one hydrogen, then the compound that has 2 hydrogens can do the most hydrogen bonding. More hydrogens per oxygen, more hydrogen bonding. The strongest intermolecular forces. So these all have the same amount of hydrogen bonding. What distinguishes them from each other? Their size. So which of these in the middle experiences the strongest intermolecular forces of this set? The far right, the largest size, the most dispersion force, strongest IMF. So this is largest size, given that it has less hydrogen bonding than water. That means this would be compound number 2. Yeah? The second strongest intermolecular forces. Compound number 3, ethanol. Compound number 4, methanol. How could we prove this? What information could we look up about these molecules to prove our understanding of their intermolecular forces? Look at their boiling points. Water boils at 100 degrees C. Ethanol is around 78. Methanol, I believe, is in the 60s. Butane boils at very, very, very cold temperatures. Butane boils lower than 0 degrees Celsius. It does not take a lot of energy for it to boil. I don't actually have those numbers written down, but it would have been smart to do so. So let's look them up together so that we can prove our ranking. Boiling point of methanol, 64 degrees C. Boiling point of water, 100 degrees C. Boiling point of ethanol, 78 degrees C. Boiling point of isopropanol, 82 degrees C. Did you find it? Oh. You thought it was what? For this? What makes you think that? It's actually negative 0.5 degrees C, which is higher than I expected it to be. Like just barely below 0. Weakest intermolecular forces requires the least amount of energy to separate those molecules. Strongest intermolecular forces requires the most amount of energy to separate those molecules. And we're saying energy despite looking at temperature because temperature is proportional to energy. Good? All right. Some implications of all of this. Viscosity. This is something I think you all have a very intuitive definition of. How do you think of viscosity? How slow something flows. I like it. The thickness of a liquid. It's actually exactly that. It's a measure of how quickly a liquid pours. And that idea of flowing, that happens only if you're pouring something, right? So how do we expect intermolecular forces impact viscosity? Stronger intermolecular forces, stronger attraction between molecules, stronger viscosity, higher viscosity, stronger IMFs, higher viscosity. More thick? Is it thicker? I don't think it's more thick, is it? Thicker liquid. Have any of you ever changed your own oil in your car? Yeah? Or seen somebody do it? Oil is not super viscous, but it's a lot more viscous than water. I guess there's another useful analogy here, which is cooking oil too. If you cook with olive oil or corn oil, those oils definitely are more viscous, but they still flow very quickly. They just aren't as thin as water. And that's because oil has higher intermolecular forces. Water has very strong hydrogen bonding. Oils pretty much only have dispersion forces, but those molecules are huge, so all of that dispersion force adds up. Per molecule, it's more dispersion forces than water's hydrogen bonding, stronger IMFs, more viscous. What's the most viscous liquid you can think of? I'm sorry? What is that? Tar. Okay, you could have just said tar. Your P confused me for a B for a second. Last week of classes, Ryan wants to go off the rails. That's fair. Yeah, it'd be a good call after you called me that. So tar, very viscous. What else? Honey, super viscous. Anything else? Yeah, that's pretty much all I could think of too. Kind of along the lines of honey would be like syrup, if it can stay a liquid, right? Sometimes it solidifies. My honey keeps solidifying and I don't like it. Two other things that get impacted. These sound very similar, but they are different. One of them is the cohesive force, and the other is an adhesive force. Think of this cohesive force as attractions between molecules. This causes them to contract. The cohesive force between molecules cohesive, you're using that same prefix there, co, as in cooperate, coordinate, covalent. That cohesive force within a sample draws these molecules together and lends itself to surface tension. So imagine a bunch of molecules along the surface of a sample. They have this cohesive force to each other, attracting them in towards one another, which leads to them forming these kind of tightly packed domes. You've seen water droplets. That water droplet is the result of cohesive forces between molecules, creating that surface tension on the water droplet. Why do water droplets form? Why isn't water just a flat puddle? Why do they pull themselves up into these domes? It means that they can actually maximize more interactions with more molecules underneath them. And surface tension is obviously unique between different compounds. One of the samples with the strongest surface tensions is actually mercury. You guys have seen mercury or videos of mercury? Anybody? Like when a thermometer breaks, and you know what happens to that mercury? Does it kind of pool and form a puddle? Or does it form little droplets, little mercury balls that just bounce all the way around? That's because mercury has such a high cohesive force that it doesn't like to form pools. It doesn't puddle. It pulls itself into very tight balls. So if we look at the surface tension for some of these compounds, water has a surface tension of about 72. This is millinewtons per meter. Gasoline has a surface tension of about 21. And mercury has a surface tension. You guys want to guess? Is it like a little bit more than water? Is it twice as much as water? 10 times as much? Almost 7 times as much surface tension as water. The difference between water and gasoline, you probably aren't used to seeing gasoline form gasoline droplets, right? They don't really form bubbles at all. The difference between gasoline and water is insignificant compared to the difference between water and mercury. Mercury has very strong cohesive forces. The next difference, or the next application of intermolecular forces is the adhesive force. Cohesive is between the same molecules within a pure sample. Maybe I should have kind of clarified that better, because here I want to say this is between different molecules. I guess I should say different types of molecules. This actually causes some chemicals to climb other chemicals or to be repelled by other chemicals. So I'm going to give you guys a diagram of a glass cylinder. And inside this glass, I'm going to place some water. And those molecules that butt up against the glass, they have a strong adhesive force with the glass. So the water molecules get pulled by the glass upwards. And this leads to the meniscus. where these molecules of water along the edge have this strong interaction with the glass, that adhesive force pulling them up the walls, leaving this divot down below. So this is water. What do you think would happen for mercury? The opposite of, well, it's actually still a meniscus. We just say a concave meniscus or a convex meniscus. Mercury, which has much, much stronger cohesive forces, will experience much, much weaker adhesive forces. So rather than being pulled up the sides of the glass, mercury will push itself down the sides of the glass, creating a bubble on the inside. Water forms a concave meniscus. Mercury will form a convex meniscus. And this does lead to capillary action. You guys know capillary action? Those of you in lab, do you remember doing the chromatography experiment? The paper chromatography. We took different pH indicators, we put them onto paper, and then we put that paper in a solvent, and that solvent was drawn up the paper. To spot those indicators, you actually use something called a capillary tube. Where else do you know the word capillary from? Anybody? Your what? Blood vessels, capillary vessels, which are the smallest blood vessels, right? They're the smallest in diameter. Where else? Capillary. Plants. Plants use capillary action to pull water from their roots up to their leaves. If you have this open-ended tube, and I'm going to try and specify that it's open on both sides, and you set this tube into a sample of a liquid, this adhesive force will pull some of that liquid up the sides to create that new meniscus. Capillary action occurs when you start to shrink this size of this tube. So instead of having a very wide tube, I'm going to create a very narrow tube, and I'm going to set that into the liquid again. We're essentially just changing the ratio of cohesive force in the water sample and adhesive force with the glass. And that allows for an even stronger capillary action that pulls your liquid further up into that tube. Not osmosis. Has nothing to do with capillary action. Osmosis is more of diffusion. So go back to our talk on diffusion for that. So that's why capillary vessels are called capillaries, because they're very, very small blood vessels. And rather than needing that force of the heart pumping, your blood can actually be pulled through those capillaries a little bit more easily with less force and just cohesive forces. Same thing for trees, which do not have hearts to put pressure into their liquids and make them move, but having very, very small tubes allows for that liquid to be drawn up more easily using cohesive forces. What do you guys think? Intermolecular forces, the biggest picture we've looked at so far. We've spent so much of this semester looking at the smallest details of atoms, talking about how electrons move between energy levels when light comes in, or how they emit light, all the way to why atoms bond with each other, and then looking at what those chemicals do in chemical reactions. And now we're looking at big scale. This is the part of chemistry that I really like because it's the most applicable to every day. One tip, though, is when I think about all this kind of stuff, I am actively thinking about one molecule in the context of billions and billions and billions of other molecules. You cannot think about intermolecular forces by only thinking about one molecule. You need to think of it as surrounded by all of these other molecules. I mean, just take 1 mole of a chemical and try to apply intermolecular forces to it. How many molecules do you need to be thinking of? Like 600 billion million molecules, right? And that's just 1 mole. That's a small number of molecules in the world of chemistry. Okay, that was module 22. Module 23 is on phase change. And of course, this will have a lot to do with the intermolecular forces inside of a molecule. But we're also going to go back to that idea of enthalpy, and we're going to look at the energy required for phase change. So I want to start by drawing a depiction of our phases and the terms that we use for them. So up here, we'll put the gas phase. On the bottom left, we'll put liquid. And then to finish this triangle, on the bottom right, we'll put solid. I've got 6 terms that I want to plug in here. So I'd like 6 different people to help me fill these in. The change of phase from solid to liquid, what's it called? Blake? Melting. There is another term that we're going to use, and I want you guys to be introduced to this now. This is also referred to as fusion. Terrible name. Terrible. I hate it anyways. Because when I think of fusion, I think of putting things together, and liquid does not make me think of putting things together relative to solid, right? It actually makes me think that those molecules are moving around more. It's more like they're drifting apart than coming together. But I want you to be aware of it. Liquid to gas. Daniel. Evaporation? True. Vaporization. Vaporization is the term. Evaporation is more of like the action. We say that a compound evaporates, and that is the process of vaporization. Yeah, actually, I'm glad you brought that up. So vaporization, the process of something evaporating. I've never actually thought about why evaporation has an E in front of it. What about backwards? When we go from gas to liquid. Cool. Condensation. A gas condenses into a liquid, and we call that condensation. You might also think of precipitation, but precipitation doesn't necessarily define the phase. We say that water in the atmosphere can precipitate as rain or sleet or snow, and those are all forms of precipitation. We also talked about precipitation reaction, where aqueous solutes precipitate as a solid. So condensation is the right term here. And from liquid to solid. I want 6 different people. Okay, we can sit here. Freezing. Good. All right, now these are the 2 that I suspect you guys are the least familiar with because they're the least common in our day-to-day lives. So from a solid directly to a gas. Ryan? He was waiting for this one. Does sublimation make you think of anything? Nice. I mean, to me, it makes me think of the word sublime, right? And what does sublime mean? Because that's actually, in the same way that we say vaporization is when a compound evaporates, sublimation is when a compound sublimes. So what is the adjective sublime? We know the verb sublime is to sublimate. What do you guys think of it when you hear, well, that's just sublime? Good or bad? Something good. Okay, so for whatever reason, this process of going from solid to gas might evoke a good feeling in you. And from a gas directly to a solid. Jacob. Deposition. And you guys probably have you've probably heard deposition used in other places, right? Anybody think of a context for deposition? Yeah, in a law context, a deposition is, I don't know, because I'm not a lawyer. It's like a court hearing or something. But what you also hear in here is deposit. Take something and deposit it. So when a solid condenses down into when a gas, I can't use condense because that's for going to a liquid. When a gas forms into a solid directly, it's like it's depositing onto a surface as a solid. Deposition. Which of these transitions, and actually you'll notice they're color coordinated, red or blue, is related to an increase in kinetic energy? Red correlates with an increase in kinetic energy. Can someone justify that? Keon. Perfect. In that solid, the molecules are not moving very much. If they're moving, they're just vibrating. They don't have enough energy to move past each other. Then they get enough kinetic energy to break some of those intermolecular forces and move past each other. Then they get enough kinetic energy to break free of each other entirely. Increasing kinetic energy is in red. If you take a gas and you release some of that kinetic energy, it will get trapped by its intermolecular forces. You pull out even more of that kinetic energy, they get stuck in place. So blue is decreasing kinetic energy. These are our phases, our phase change. I want you guys to be familiar with them. You're already familiar with most of them. Now you know there's some weird ones. Do you remember at the beginning of the semester we said these are not the only phases? There's another phase that's referred to as plasma, but plasma is really just ionized gases. So plasma is basically just gas. But there's actually, we're going to look at phase diagrams in a bit, and there is another phase called the supercritical phase. I want you guys to recognize that we are essentially drawing lines in the sand and putting these definitions in it, and nature doesn't always adhere to our lines in the sand, right? So there are more phases than what we like to describe, and so those phase changes might have different terms to them. All right, let's talk about the energy required for some of these phase changes. We'll start with the enthalpy of vaporization, which we can write as delta H vape. Endothermic or exothermic? Raise your hand for endothermic. Raise your hand for exothermic. Good. Vaporization is associated with an increase in kinetic energy. That means your system, the compound that is being vaporized, is absorbing that energy. Enthalpy of vaporization is always positive. If we wrote a physical reaction, I almost called it a chemical reaction, but it's really not a chemical reaction. And we said liquid water becomes gaseous water. That's the equation for our enthalpy of vaporization. The only thing that changes, not a chemical, the only thing that changes is the phase of matter. Enthalpy of vaporization for this is positive 44 kilojoules per mole. Per mole of what? We talked about this with enthalpy in Unit 8, right? Per mole. There's more than one right answer, so take a stab at it. You guys remember what we said in enthalpy? Could I say per mole of reaction? Because that's what enthalpy is always referring to. Whatever equation is written, I mean, it would be weird to say reaction here because there's not like a chemical change. Whatever equation is written, it's per mole of that equation. Could I say per mole of gaseous water formed? Yeah, because that agrees with the equation as it's written. Could I say per mole of liquid water vaporized? Yeah, because that agrees with the equation. Could I say per mole of atomic oxygen, O2? No, because that's not involved in this equation at all. So again, most important thing that I want you guys to think of when you see per mole is per mole of whatever that chemical equation is as written. We don't have any coefficients here, or I should say all the coefficients are 1. But that vaporization enthalpy, it always goes with it. How does the relationship between vaporization relate to the enthalpy of condensation? Would this equation make sense to relate the enthalpy of vaporization and the enthalpy of condensation? Yeah? They are equal to each other? Inversely, equal and opposite. So we're missing a negative sign. The enthalpy of vaporization is exactly opposite of the enthalpy of condensation. That's to say that I can take this equation and I can just write it the other way around. Gaseous water becomes liquid water. This is no longer the enthalpy of vaporization because I'm not looking at a liquid to a gas. This is the enthalpy of condensation, which is now negative 44 kilojoules per mole of that reaction. Yeah. Okay, so it takes some energy to become a gas. Energy is given off when a gas becomes a liquid. Here are some of the other enthalpies. Enthalpy of fusion, which is also called what? Melting. We're going to write it as delta H fuse, F-U-S, positive or negative, endothermic or exothermic. Good. Little movement in the molecules being able to move past each other. Endothermic. Let's take another example for water. Do you suspect that solid water becoming liquid water has a higher enthalpy, approximately equivalent enthalpy, or a lower enthalpy than its vaporization? How do you think enthalpy of fusion relates to enthalpy of vaporization? Sorry? Same? You want to take these solid molecules locked in place next to each other, and you want to get them to move past each other. Fusion. Or you want to take these molecules that are able to move past each other, and you want to pull them apart and send them to space. Vaporization. Does one take more energy than the other? If so, which one? Or are they about the same? I'd like to hear you debate. Okay, Ryan's changed his position. Okay. Your reading would be a good place to back up your answers if you've done it. Yeah? Liquid to gas, a lot more energy. Does that feel justifiable? Do gaseous molecules experience intermolecular forces? Certainly not the ideal gas. Kinetic molecular theory says that the ideal gas doesn't interact with other gas molecules other than through inelastic collisions. So they're not being drawn towards each other by their intermolecular forces, whereas liquids are constantly interacting with intermolecular forces, and solids are as well. So the only difference between solid moving to liquid is that you just have a little bit more energy, but you're still held by intermolecular forces. Liquid to gas, you are completely overcoming those intermolecular forces. So it does reason that it should take a lot more energy to vaporize a compound and a lot less energy to fuse it, melt it. Our enthalpy of fusion here is plus 6 kilojoules per mole. So what is my enthalpy of freezing? -6. You'll see this written sometimes as FRZ, -6 kilojoules per mole. Now the last one is the enthalpy of sublimation. Delta H sub, endothermic or exothermic? Raise your hand for exothermic process. Raise your hand for endothermic process. Ooh, not as many hands. You want to justify it? Yeah. Taking those solid molecules and then just directly turning them into gases. You need to increase that energy, endothermic. Water doesn't, we don't often think about the sublimation of water. So instead, let's look at the sublimation of dry ice. Solid CO2 to gaseous CO2. Here's another spot I'd like you guys to try and think about. How would this sublimation energy compare to our vaporization and our fusion energies? Bigger than both? Makes sense? I mean, you're going from a solid directly to a gas without going through that liquid state. And we do have to recognize that this is a different chemical, right? So we're not talking about the sublimation of water anymore. We're talking about sublimation of something else. So do you feel like that could make an impact on the energy of sublimation needed? Like maybe if we were staying consistent and we looked at the sublimation of water, we'd say something else. But do you still think for a different chemical, CO2, that energy of sublimation should still be fairly high? This is about 26 kilojoules per mole. And I do want to point out, it's not water, so we're looking at a different chemical. But that energy of sublimation falls in between water's fusion enthalpy and water's vaporization enthalpy. But carbon dioxide only experiences dispersion forces. It doesn't have to overcome any hydrogen bonding forces like water does. So it does take energy to go from solid directly to gas. It takes more energy than water going from solid to liquid, but it takes less energy than water going from liquid to gas. Still energy required, a good amount of energy, but because there's only weak intermolecular forces, it's not a crazy amount of energy. This is a weird thing. I don't actually have the reverse. For whatever reason, your textbook gives this example of the inverse of vaporization, the inverse of fusion, and it doesn't talk about the inverse of sublimation, but we could say delta H deposition. For this compound, it would be negative 26 kilojoules per mole. Of course, the enthalpy of deposition should always be equal and opposite to that. All right, I want to give you guys a break. During that break, I'm going to put up a problem on the board that uses Hess's law, where I want you guys to predict the energy of sublimation for water. So I'll get that started. Take a 5-minute break. Let's be back in here at 10 after 11 to finish this module. All right, as you guys settle back in, I want you to see if you can use Hess's law to solve for the enthalpy of sublimation for water. Does anybody know Hess's law? Do you remember learning about this? We talked about Hess's law in the context of enthalpy. What we said was the sum of the parts is equal to the total, which is like a very intuitive law, right? Of all of the laws you've ever learned, this probably makes the most sense. We actually used it when we were doing solving for like enthalpy of formation equations. If I don't know the enthalpy of formation of a specific thing, I might be able to solve for that by the enthalpy of formations of different things that lead to what I want. That means that I can add these equations together. So Hess's law here is saying that I can take the enthalpy of fusion, solid water to liquid water, which has a value of plus 6 kilojoules per mole. And I can take the equation for enthalpy of vaporization from liquid to a gas. For water, this has an enthalpy of plus 44 kilojoules per mole. And Hess's law says I can sum these together. Different components, add together and subtract. You'll notice that we'll have to set the arrows equivalent to each other. This is basically like an equal sign. H2O solid only shows up once, and it only shows up on the left-hand side of the equation arrow. That means H2O solid comes down on the left-hand side of the equations arrow. H2O liquid shows up twice, once on the reactants, once on the products, once on the right, once on the left. So H2O liquid cancels. H2O liquid subtracts itself out of this equation. H2O gas only shows up once on the right-hand side, so the sum of these two equations is solid water moves to gaseous water. And you can see it's visualized there. If I take water from solid to liquid, that takes a specific amount of energy. And if I take that liquid now to a gas, that takes a specific amount of energy, which must be equal to taking that solid directly to the gas. So now I sum these two enthalpy values. I get the new enthalpy of sublimation, positive 50 kilojoules per mole. Does it surprise you how close the enthalpy of sublimation is to the enthalpy of vaporization? I mean, they're just right next to each other. It takes a lot of energy to go from liquid to gas. It doesn't take that much more energy to go from a solid to a gas. If you're already overcoming all of that hydrogen bonding force, it doesn't matter whether you're at a solid or a liquid state to begin with. It takes a lot of energy to overcome that and become a gas. So our Hess's law prediction says the enthalpy of sublimation is 50 kilojoules per mole for water. Good? Okay, here's a good application of these enthalpies. Let's look at heating and cooling curves. I want to show you guys what this looks like first, and then I want us to sketch one out ourselves so that we can talk about the math that goes into it. Oops, I'm on the far end. On this curve, on this graph, we're looking at solid water, some ice. And it's telling us that our temperature is at negative 10 degrees Celsius. So on our graph, we're looking at the temperature of that sample on the y-axis and the amount of heat that's added, the amount of energy provided to the sample. First of all, the phase change for water doesn't happen at negative 10. So this ice needs to be warmed from negative 10 degrees up to 0 degrees C before it has enough energy to go through a phase change. So we add that energy. The energy that's added goes directly to the temperature of the ice. And you'll notice it's still ice, it's just now at its phase change temperature. As we start adding more energy, the temperature won't change. You'll notice now that the ice has begun to melt. So I have some liquid and I have solid still. My temperature is still at 0 degrees C. That liquid and that ice, that liquid and that solid are at the same temperature. The energy that has been put in is only going into changing the phase, right? That's to say, this is where the energy is going into the enthalpy of fusion. Now, I transition so that all of it has been melted, took some amount of energy without raising the temperature just to melt it. As I start increasing the energy more, I raise the sample of that water to 50 degrees C, no phase change yet, provide more energy. Now I've reached 100 degrees C, still no phase change. The water is only at enough energy to start going through a phase change. Now as I add more energy, my temperature doesn't change. As that liquid turns into a gas, the liquid and the gas are both at 100 degrees. That energy now is going directly into the enthalpy of vaporization without changing its temperature. Have you guys ever heard that it's harder to cook noodles at elevation? That it takes longer to boil your pasta when you live in the mountains versus when you live at sea level? No. Water boils at a lower temperature at elevation. We're actually going to talk about phase diagrams too in a minute. Which means that when you are providing energy to your pasta in the form of boiling hot water, you are providing less energy to the pasta because it's boiling at a lower temperature. Would you rather provide energy to your pasta at 95 degrees Celsius or provide energy to your pasta at 100 degrees Celsius? When you have boiling water, you are at a specific temperature, and that temperature is different depending on your pressure, which is why they say you can cook your pasta faster at sea level because you're boiling your water at a higher temperature. All of the water sits at a higher temperature, providing more energy. So no phase change. After all of that liquid becomes a gas, now that gas can start absorbing more energy beyond 100 degrees C. This is actually why hot water is less dangerous to you than the steam that comes off of it. You can put your hand in boiling hot water. I don't recommend it. You can put your hand in boiling hot water and it will do less damage than the steam that sits above the boiling hot water because that steam can pick up additional energy beyond 100 degrees C. You'll get burns either way, but you get burned worse from steam than you do from water because steam can go beyond that phase change temperature. It's only until all of that liquid has turned into gas that that gas can start to pick up extra heat. In theory. In practice, some of that gas actually is way above 100 degrees C. Okay, so I want to go through some of the calculations for you, with you. We're actually going to measure how much energy is required. So let's say that I have a 100 gram sample of water, temperature in degrees Celsius. We'll do the same thing. We'll start at negative 10 degrees C, and the first change that we're going to take it to is 0 degrees Celsius. Let's do this in a different color. How can I calculate the heat, the energy required for this temperature change? Do we have any tools to help us do this? Do you know what's going to be easier? It might be easier to do 180 grams of water. When we do the phase change, we're going to have to go by per mole, and 180 grams of water is exactly 10 moles, so it makes the numbers a lot easier to do. Heat based on temperature change. Q equals M times C times delta T. Haha, you thought it was gone. It's not gone. It's just now in a different application. What is M in this context? 18. 180 grams. C? C is that specific heat. And the specific heat of water is one that I've recommended that you write down and bring on your cheat sheet. 4.184 units are crucial here. Joules per gram degree C. This is how much energy it takes to heat 1 gram by 1 degree C. But I'm not heating 1 gram, I'm heating 180. And I'm not heating 1 degree C, am I? What is my temperature change for the water? -10 is my temperature change. I'm cooling it. Yeah, I'm going from -10 to 0, so I'm increasing the energy by 10 degrees C. Remember, system versus surroundings means in the context of the calorimeter, I might be seeing a different temperature change, but I'm actually looking at the temperature of my water. Grams cancels, degrees C cancels. I've calculated a value here that is unique in joules to the heating of this sample of water. 180 times 10 times 4.184. That's 1800 times 4.184. Tell me if you guys get the same. 7,500 joules. I'm rounding a bit there. 75.31 joules. I'm not going to take all the decimal places because we're going to round to some significant figures at the end of this all. 7.5 kilojoules is what it took just to bring that water up to temp. Now, I won't see my temperature change while I boil it. While I melt it. How can I calculate the energy here? You look at it and then you see it. Okay. How about I use my enthalpy of fusion, which says it takes 6 kilojoules per mole of reaction, and the mole of reaction conveniently is written as per mole of water. So I've got 6 kilojoules per mole. Am I heating 1 mole? How many moles of water am I heating? 10. Now, I'm going to skip that busy work. 180 grams divided by 18 grams per mole gives me 10 moles. But that allows me to cancel my units of moles and get into units of kilojoules. So that's 60 kilojoules. All right, I'm going to make an executive decision. I'm going to erase what I had over here in joules, and I'm going to rewrite it. Because I want to match my units, and I don't want to have to go through this later. I'm also going to limit some of my sig figs because I can see that the enthalpy of phase change is going to be a lot higher than the enthalpy of heating the temperature. So I'm going to write this as 7.5 kilojoules. And you'll notice that that is much, much smaller than the enthalpy of fusion here. Now, I'll bring my temperature up to 100 degrees C. How do I calculate the energy required here? Same equation. Q equals mass times specific heat times the change in temperature. We've already looked at how to change the temperature of it. This time, it's 180 grams of liquid water times 4.184 joules per gram degree C. What is my temperature change? $110. No, just 100. From 0 to 100, temperature change of 100 degrees C. All right, I do have to say something. I might have jumped too quick. The specific heat of solid water might be different than the specific heat of liquid water. I didn't think about that. If this were a problem given to you, they would give you that number, but I forgot to look for it. So we're kind of making an assumption there. We might be off by a little bit because of that assumption. Here, when we plug this in, do I really need to pull out my calculator? Why not? So it's, 10 times larger than this temperature change. That's all. This equals 75 kilojoules. When in doubt, don't hesitate to pull your calculator out. Just plug it in, right? But look at that. All you're doing is multiplying it by 10. Now we vaporize. Once again, I'm going to need to use the enthalpy of vaporization. And I want to point out something. I showed you guys this change here. I started with a piece of information that had 2 units. And I normally tell you guys to do dimensional analysis by starting with information that has 1 unit. I actually multiplied by that information that had 1 unit. And that's because pieces of information with 2 units can be flipped upside down depending on how you need to use it. It's never a bad idea to just take what makes sense to you, plug it in, and if you realize your units are all upside down, just start over by flipping everything over. Don't get caught up worried about, I'm not sure exactly where to start. Just take a stab at it and see where it brings you, and then come back in and make the adjustments you need. So I'll show you how we can do this by starting with the piece of information that has 1 unit. I have 10 moles of water, and it takes 44 kilojoules per mole to vaporize water. That gives me 440 kilojoules in this vaporization step. Do you want to go beyond? Can we just leave it here? How much heat did we actually add? Well, we added 7.5 kilojoules during fusion, 60 kilojoules 7.5 joules while warming the ice, 60 kilojoules during fusion, 75 kilojoules while warming the water, and 440 kilojoules to boil it. So now you can go home and tell mom, or dad, or yourself, how much energy it takes you to boil that hot water to get your pasta ready. Just measure how much water you're using. And then plug it in. And you can calculate for yourself how much energy it takes to get all of that water boiling. What makes the biggest impact here, by the way? Where is the majority of this heat coming from? Or going to? Yeah, it's that vaporization that requires the most energy. 440 and 60 is 500, 575, 582.5. Lot of heat, most of it from the vaporization. Cool. Do you guys have questions on this math? And I did make a mistake. Specific heat of melting, specific heat of ice, much, much lower than the specific heat of liquid water. So if we want to make that change, that was right here. This should actually be 2.09. What impact does that make? 180? Okay, so instead of 7.5, it's 3.7 or 3.6, 3.8. I think I got, this is going to round to 3.8 kilojoules, which means I'm just, 3.7 lower? So 500, I don't know, let's just round it and say about 578. Let's round it to 2 sig figs, and let's say the enthalpy is about 580 kilojoules to heat this water. Within reason to round it to that. Okay, that was an important slip up on my part. You know what happens when you assume a value? It makes an ass out of you and me. But in the long run, that impacted the smallest amount of energy, and within rounding had almost no meaningful significance on our final value. All right, there is a new concept here called vapor pressure. This takes us back into conversations we had during our gas law unit. Vapor pressure is a little redundant. That's just the pressure of a gas. But we're talking in context here saying that's the pressure of a gas sitting over a liquid. What is that liquid's vapor pressure? Interesting, right? To say I have a liquid sample, what is the pressure of its gas sitting over it? Here's how I like to demonstrate this. Let's look at a snapshot of a liquid. Okay, I'm highlighting these 4 molecules. At any given time, there are molecules of this liquid sitting up here in the gas phase. Gas on top, liquid on the bottom. And of course, there are a lot of these molecules sitting beneath it in the liquid phase. Depending on the chemical, the amount of gas sitting above the liquid surface changes. We'll talk about what impacts that. Equilibrium vapor pressure says at any given time, there is some amount of gas molecules above that liquid. But this is a dynamic equilibrium. What is dynamic trying to tell you? Movement, change. And equilibrium is trying to tell you stays the same, unchanging, equal at any given point. Dynamic equilibrium is the process by which things change and still stay the same. So let's imagine that there's a molecule of this liquid moving very fast, and it rams into a molecule sitting on the surface. It has now provided the energy needed for that molecule to vaporize. It has overcome its intermolecular forces with its neighbors, and it is moving into the vapor above the liquid. At that same instance, this gas molecule is also moving very fast, and it slams down into the surface of the liquid, lodging itself between intermolecular forces, getting trapped. So if this is instance 1, instance 2 looks like this. Things have changed. Gas molecules have come into the liquid. Liquid molecules have gone up into the gas. And yet, things stay the same. The same number of gas molecules, the same number of liquid molecules. These molecules give it the vapor pressure. And that pressure is constant, equilibrium. At all times, at the same temperature and pressure, that vapor pressure is always the same. And yet, the molecules making that vapor pressure change. Different molecules are moving in and out of the surface at different times. A dynamic equilibrium. The more things change, the more they stay the same. Here are the implications of intermolecular forces on this vapor pressure. With increasing intermolecular forces, we see decreasing vapor pressure. Why? It's harder for any of those molecules at the surface to escape. They've got stronger attractions to their neighboring molecules, so it's much less likely that any of them will escape those intermolecular forces and sit as a vapor. With decreasing IMFs, we see increasing vapor pressure. Molecules that don't interact with each other very strongly sit more above the surface of the liquid, take less energy to go into that vapor state. And then one last big implication about vapor pressure. Vapor pressure is not always the same. As you change the temperature, the vapor pressure changes. So I want you guys to make this prediction. With increasing temperature, how will vapor pressure change? What is temperature equivalent to? Energy. What does energy allow for these molecules to do? Move more. Which means more of a chance that they move away from their intermolecular forces, more chance that they have an escaped velocity out of the liquid and become a gas. So with increasing temperature, increased vapor pressure. I didn't mean to abbreviate temp as TEM. Increasing temperature, increasing vapor pressure. Until you get to a point at which the vapor pressure of the liquid, the amount of that liquid that is actually, the amount of that compound that is sitting as a gas over the liquid, is equal to atmospheric pressure. This we call a boiling point. This is when vapor pressure is equal to atmospheric pressure. That's to say that the atmosphere's gas sitting on top of your liquid has no more of an impact on that liquid than the molecules of the gas themselves. The liquid is in total equilibrium with gas. The liquid is able to completely turn into gas molecules. The gas molecules of the atmosphere are no longer suppressing the substance and keeping it as a liquid. Those molecules have enough energy that they can phase in and out between solid and liquid. So there are some diagrams for this. I don't always like them because they look a bit confusing. So I want to show you guys one and talk about it. I may not have you draw it into your notes because I'm not sure that they will add much to your understanding in your notes. So I want you to see it so that you know what it looks like. Here's that conversation we were having. A liquid has molecules escape. now you've got those molecules sitting over the surface as vapor pressure. Different molecules, different vapor pressures, and the explanation of why vapor pressure increases at higher temperatures. There is now a larger amount of gas molecules with the energy needed to become a gas. And this is what we call here we're just looking at a comparison of pressure versus temperature for different chemicals. Here's water. Kilopascals, we're looking at 101 kilopascals is 1 atmosphere. We actually, in Salt Lake City, we have a little bit less than 1 atmosphere as our typical pressure, but 1 atmosphere would be sea level pressure. And you can see that that 1 atmosphere corresponds with 100 degrees C. At lower pressures, so we're down here, closer to maybe 90 kilopascals, you can see the vapor pressure is actually a little bit lower than 100 degrees C. So we can boil our water lower than 100 degrees C. That would mean less energy to boil the water. But your water now has less energy to pass on to the noodles. So you will boil your water faster. You will take less energy to boil your water. You will provide less energy to your noodles as a result of that. And there are ways to change that. Are you guys cooks? Do you know how to increase the energy you give to your noodles while you're boiling them? Add salt. And that's a Gen Chem 2 concept. So you'll have to go on to Gen Chem 2 to see why adding salt increases the boiling point. I'll give you a hint. It's because now there are less molecules of actual water at the surface. Where's my diagram? There's less molecules of water, and now there's molecules of salt. And so the odds of a molecule of water being at the surface and vaporizing are decreasing. So the energy to increase the odds, to increase vapor pressure, goes up. Anyways, I'll leave that for Gen Chem 2. Here's why I don't like this. A lot of these curves have these lines that just kind of, they go to 0 degrees C, but we know that there are negative degrees C, and it just doesn't show it for whatever reason. So these graphs, they compare the vapor pressures at different temperatures for different compounds. I don't find it useful to be in your notes. When you see a problem on RealChem that deals with it, you'll know. Instead, I want to bring us to this. This is a phase diagram. Phase diagrams compare phases at different pressure to temp combinations. Now, I will admit, the more time you spend with phase diagrams, the easier it is to remember which axis is pressure and which axis is temperature. But if you're not regularly reviewing phase diagrams, it can be really hard to remember, am I looking at pressure on the y-axis or temperature on the y-axis? I don't really have a good answer for you there. So those of you that have aspirations of going to medical school or anywhere where you might have to take an entrance exam that reviews general chemistry, it's very likely you'll see a question like this, and you may need to remember what these axes mean. So come back and review these, because there's no intuitive way, at least in my opinion, to make sense of this. Pressure along the y-axis, temperature along the x-axis. This specifically is the phase diagram for water. Other phase diagrams look a bit different. And there's a few important components on this phase diagram that I want you guys to recognize. Low temperatures and high pressure, that's a solid. Low pressure, high temperature, that's a liquid. Somewhere in between. Oh, you know what? That sounded really weird when I said it. Low pressure, high temperature. That doesn't even make sense for a liquid. That's your gas. Somewhere in between, that's your liquid. Right here, where all three of these lines meet, this is called a triple point. So you know the characteristics of freezing water. A liquid starts to that liquid starts to expand and crystallize. It becomes a solid. You know the characteristics of a melting ice cube. It gets wet on the outside. It starts to drip. You know the characteristics of boiling water. Bubbles form inside of the liquid and it boils. At this temperature and pressure, all of those phase changes can happen at the same time. A solid can go directly to a gas to a liquid to a solid to a liquid to a gas. You will typically see characteristics of all three phases at the same time. You will see the water boiling with ice inside of it. That's a triple point. It's an odd phenomenon. But again, we drew these lines in the sand and we said, when it looks like this, when it behaves like that, we call it this phase. The triple point disagrees with any of that and says it's just water. It's just whatever chemical you have. At this point, we see the critical point. Beyond the critical point, beyond that temperature-pressure ratio, it just becomes a supercritical fluid. It is no longer a liquid or a gas. It's a different type of fluid. It has properties that are not related to those of gases or those of liquids. You might call that a different phase, a supercritical phase. There are some really cool videos. Maybe I'll start class on Wednesday by showing some of those videos. Cool videos of people that get up to those high temperature and high pressures. And you can see how it kind of just looks like a flowing cloud. It's not quite clear. It's not quite opaque. It's a little bit foggy. And it clearly has some viscosity, but there's no layer that is gas or liquid. It is all one supercritical fluid. Very interesting stuff. Beyond this, we have one equation to talk about, and we're done with Module 23, which means on Wednesday, we'll talk about that equation. I'll show you guys some fun videos. And then we have Module 24, which is the only module in Unit 10 that we're doing. And that's it. And I don't see any reason why we can't get through that on Wednesday. So we'll be done for the semester with new material on Wednesday. I'll open up your final unit test for this Thursday, and I will leave it run for a week longer than it's predicted on the schedule, right? That gives you a lot longer to actually do it and start preparing for the final. All right, thank you guys for the time. I will see you on Wednesday.